Bam! Mr. Tarrou, in this lesson we are going to, algebra lesson, we're going to be looking at the definition of a linear function and the attributes of their graphs. Is the function increasing? Is it decreasing? Is it constant? Are there any absolute or relative max or mins? Stuff like that. We're going to be looking at interpreting defining and interpreting slope and y-intercept in the context of a real-life application. And at the end of this lesson, we'll be looking at, just reminding you that there's some other forms of lines than the one that we'll be discussing in this particular lesson. Now, I've already got a lot of examples, a lot of lessons about lines, because you use lines in algebra, algebra 2, you use it in a little bit in trigonometry, and you even use linear functions and need to understand linear functions quite a bit in statistics and even in calculus when we find slopes of tangent lines. Okay, so yeah, so I have a lot of lessons already of just the mechanical use. Here's an equation, graph it using slope and y-intercept, or here's an equation, graph it using the x and y-intercepts. What's the relationship visually and mechanically between parallel and perpendicular lines and such. And you're going to find links to all of those lessons I've already done in the description of this lesson. We're going to, in this lesson, look heavily at how these linear functions can represent real-life applications and, and like I said, interpret the slope and y-intercept in context of those word problems. Okay, so, and we'll also do a little bit of practice of finding slope, given a couple of points, and the one example on the next screen, which will be, again, that word problem, we'll graph that linear function using x and y-intercepts. Definition of a function f is linear if it can be expressed in the form of y is equal to mx plus b, where m and b are real numbers. Now, if you have any experience with lines already, you'll understand or recognize that y equals mx plus b is the slope-intercept form of a line. There's also other forms of lines. There's point slope form, there's standard form, but our definition here is specifically using the slope-intercept form of a line. And even before you get it written in this exact form, which we like very much because it's very easy to graph a line when it's in slope-intercept form, look at your equations and see if it has the variables of x and y in it, and are the exponents of those variables a positive 1? If so, you're going to be looking at a linear equation. Now, in this slope-intercept form, in this y equals mx plus b, where m and b are real numbers, m is a variable that we sort of save, a letter that we save in algebra to represent slope. So m is always going to represent slope. It's just not going to be like a random a, b, c, d, x, y type thing. M always stands for slope, and slope is rise over run. How far, when you read a graph left to right, how much must you rise, go up or down, and then how far over to the right do you need to go to get from one point to another, which is on a line. Now, rise is a change in the vertical direction. Remember, the horizontal axis is the x-axis, and the vertical axis is the y-axis. They might have some other names if you're specifically looking at an application problem, and we'll talk more about this after I get the phone. Alrighty then, so slope is rise over run, change in y over change in x. For application problems, a good definition of slope is the average change in the dependent variable that is going to be graphed on the vertical axis, or generally we call it the y-axis, right? Per 1 unit of change in the independent variable. This is going to be very important. Understanding and knowing this definition on our next screen when we get to the application problems, we'll be looking at the relationship between the number of registered boats in Florida and the number of manatees killed. And when you get into your studies of statistics, this definition, because all of statistics is about modeling and analyzing real-world data, this is the definition for slope, which we really need to use and understand. Now, for just basic graphing, like you'll see in the lessons below, like graphing in y equals mx plus b form, or graphing with x and y intercepts and such, for just graphing purposes, rise over run is a great definition of slope. You plot a point, usually it's going to be the y-intercept first, but you plot that point first, and then from that point you go either up or down, and then to the right a certain distance you rise and run, and then you plot another point and draw the line through those 2 points. But it's not a good definition for interpreting slope in real-life applications. In linear functions, the slope is constant. It never changes for a line. in calculus, you'll start to learn how to find the slope of a curve line at a particular point. So regardless of what 2 points you use to find the slope, you will always get the same answer, again, for linear functions. B is going to be that constant at the end of our equation, no variable attached to it, is going to be our y-intercept. Again, that's only if you're looking at y equals mx plus b. Will that constant that's off by itself be the y-intercept? Now, when you have a line cross, or any graph for that matter, cross the y-axis, when you're crossing the y-axis, the x-coordinate is going to be equal to 0. So every y-intercept is written in the form of 0, comma, b, because x has to be 0 if you are, again, crossing the y-axis. In application problems, sometimes the y-intercept has a real-life meaning, sometimes it doesn't. So the y-intercept often does not have meaning in the context, again, of a word problem of a real-life application. When you're graphing, it's always, well, that's where the graph crosses the y-axis. Now, again, I have a lot of lessons in the description of this video about just basic, algebraic, here's an equation and let's graph it. And you'll see me doing some examples of finding slope in those videos, but I want to just add a little bit extra here so you get, hopefully as much as you need in one lesson instead of having to bounce all over the place from video to video. So if a graph, if a linear function falls to the right, that slope is going to be negative. If it rises to the right, that slope is going to be positive. If you have a line which is horizontal, that slope is going to be equal to 0 because there is no rise. If I want to go from this point to this point, there is no rise to get to that point which is to the right. There's only a run value. So there's a rise of 0 and a run of whatever, giving you a slope of 0. And if you have a line which is vertical, that slope is going to come out to be undefined. Because, again, and let's just start with the orange line, rise over run. If the line is vertical, well, let's take a look at what that would be. This coordinate is going to be to the right 3 and up 3 from the origin. So that point is 3, 3. And this point is over 3 and down 2. So this coordinate is 3, negative 2. Okay. Well, now that I have these 2 points labeled, and let's just call this point 1 and point 2. Doesn't matter how you label them, and run through this formula for finding slope. Well, slope is y sub 2 minus, actually, let's do this. There's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Really, you should always put a set of parentheses where there's a variable in an expression when you start to substitute into it so that you don't make any, well, try to help prevent making any sign errors. So y2 is negative 2. Y sub 1 is 3, x sub 2 is 3, and x sub 1 is also 3. And when we work that out, negative 2 minus 3, when you're combining numbers with the same sign, you want to add those numbers and keep the sign. Or, of course, you can think of it as moving on a number line. I'm 0, I move left 2, and I move left 3 more because they're both negative. And we're at negative 5, 0. See, you can't divide by 0. There's no run. And so because there's no run, all vertical lines, whether it's here or somewhere else, are going to have a slope which is undefined. Well, I'm not going to get that entire word up there, so let me just write UND for undefined. This other line, as you read it left to right, seems to be falling, going down. The y values are decreasing as the x is increasing. So I think when we find the slope of that white line that it should come out to be negative. Okay, good enough. Well, we need to identify a couple of points, and I'm not doing this on graph paper, so I'm identifying the 2 points that I want to use with some white dots just so that they're clear. Negative 4, 2, left 4 and up 2 is negative 4, 2. We're going to call that point 1. And this point over here is 3, negative 1, because from the origin it's right 3 and down 1, and that down movement it shows up as a negative y. We're going to call that point 2. And let's work out the slope formula. So m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So y sub 2 is negative 1. Y sub 1 is 2 over x sub 2, which is 3, minus x sub 1, which is negative 4. Okay. If you're not using parentheses, some students will see that that says negative 4, and they'll write 3 minus 4 because they see the negative 4. But there is a minus from the formula, and then there needs to be another negative sign coming in from, well, the negative 4. And those two negatives together are going to cancel out, making a positive. And so if you don't use those parentheses, you have a good chance of making a sign error. Now, why are these two negatives canceling out to make a positive? Because there's really kind of like a negative 1 sneaking in there between the negative and the parentheses, and negative 1 times negative 4 is positive 4. So those are going to cancel, those negative signs are going to cancel out, making it a positive. And we get negative 1 minus 2 is going to be negative 3 over 7. So we have a slope of negative 3/7. Now, I'm telling you that it doesn't matter how you label these points. You know, what if we called that point 2 and called this point 1? Well, then y sub 2, which is 2, minus y sub 1, which is negative 1, over x sub 2, which is negative 4, minus x sub 1, which is 3. And these two negatives, again, are touching, and there's not much else going on there, so those two negatives are going to multiply together to give you a positive, and 2 plus 1 is 3 over negative 7. Now that looks just a tiny bit different because now my negative is in the denominator, where in the first answer version of the answer, the negative was on top. It doesn't matter where the negative is. That's negative 3/7, that's negative 3/7, and that's negative 3/7. It's all the same. And you can also tell what the slope is, if you already have a picture, by, again, reading left to right, how much up and down do you have to go, and how much to the right do you have to go? Well, that's down 3 and over, starting from here. Don't count when you touch the first point. Now you count when you move. 1, 2, 3, 4, 5, 6, 7. So there you go. The slope is negative 3/7, and that is about all I can say for defining what slope is and what the y-intercept is. Let's get to the next problem and interpret it in a real-life setting. When looking over data from 1991 to 2014 about the number of manatee deaths per year caused by boats, which will be expressed in tens of thousands, you see the following linear equation. Y is equal to negative 120 plus 2.4x. In 1991, there was 65,000 registered boats, and in 2014, there was 85,000 registered boats. So we're looking at our equation here. Y is equal to negative 120 plus 2.4x. We've got y by itself. We see that the exponents of our x and y variables are both just 1. This is written with the negative 120 is first. The b value is first. Most just regular algebra books will write y equals mx plus b, and that is the standard form of slope-intercept form. When you're doing statistics, because I teach AP statistics as well, my AP statistics book for the least squares regression lines always have them written as y is equal to a plus bx, or with the variables that we're using, y is equal to b plus mx. So this 2.4 in front of the x is going to be the slope, and the negative 120 is the y-intercept, the constant that's off by itself. I'm going to move out of the way. I want you to kind of maybe, if you would like, I'd like you to try and practice, pause the lesson, and with those definitions that were on the previous page, and just kind of thinking about what's going on here, what do you think the interpretation, the correct interpretation for the 2.4 would be, and the negative 120? Now, before I step off and do that, remember, let's do this. Let's read the problem and try and find the independent and dependent variable. What's going to be the x and the y? So we're looking over the data from these particular years. It's the deaths per year caused by But, well, it's right there. It's the number of deaths per year is being caused by, so it's dependent on the number of boats. So here's what we're comparing, and we will do we will graph this as well. I'm not sure. Maybe I wonder if I should graph it before we try and interpret the slope and y-intercept. But I think we're going to do the interpretation first. Those are our two variables. Which one of those is independent and dependent? Which is helping to explain a change in the other? Excuse me. Those boats are helping to determine, they're the cause of, at least in this particular study, the deaths of the manatees. So the boats are going to be the independent variable, meaning it's going to be along the x-axis, and the deaths per year will be the y-axis. So interpret the slope and y-intercept if you can. Alrighty, let's see what we got. Well, I wrote y is equal to negative 120 plus 2.4 into function notation. We just did that in a previous lesson where, and this is more like how many people, how people talk. Okay, y is the dependent variable, so it's the number of manatee deaths, and it's being explained by, in the study, the number of boats that are registered, which is then negative 120 plus 2.4 times the number of boats. It just looks a lot better without just those generic x's and y's. So that slope, rise over run, okay, yeah, that's great for graphing, but the average change in y per 1 unit of change in x. So the slope of 2.4 means that on average, that's important because if you look at, if we had all those original, I'm sure if we had the original data where this regression line came from, this is real life. It's not going to be a perfect line. So this line is modeling some probably some data which is appearing to be a little bit random but has a linear pattern to it. So it's about that average amount of change. So 2.4 means that on average 2.4 manatees are killed per year for every 1 unit of increase in x, the average change in y per 1 unit of change in x. Well, now I'm kind of like I started off the sentence, put it in context of the problem, the number of manatees killed, but then I just finished with an increase in x. Well, that's not in context yet. So since x is in terms or in tens of thousands for the number of registered boats, that means that we're talking about 1 unit of increase in x means 10,000 newly registered boats. And that's where, understanding the units of measure for the variables that are put along your graph, the x and y axis, you need to pay attention to that. It's not, it's not every 1 boat, it's every 10,000 boats. And this writing x in terms of tens of thousands is just to keep the number small and a little bit neater, a little bit easier to graph on an xy axis. So for every additional 10,000 registered boats, there will be, on average, 2.4 more manatee deaths per year caused by boats. And really this last sentence is what I think is the best summary of what the slope of 2.4 represents. But I wanted to lead you right through that definition, average change in y per 1 unit of change in x. Just 1 unit of x on this particular example is 10,000 boats. If there are 0 boats, oh yeah, so the y-intercept. So we put a really good context to what that 2.4 represents, the slope. Now the negative 120, okay, so y-intercept, it's a y value for when x is equal to 0. And since the number of boats is the x-axis, or the x variable, that means that for that y-intercept, x has to be 0. The number of boats has to be 0. Well, if there's between 65,000 and 85,000 registered boats, then that means really this data that we have this regression line based off of is coming from data between the x values of 65 and the x value of 85. Again, because it's in tens of thousands. And an x value of 0 is very far away from that, so we can't really have much trust in what it's going to tell us. If there are 0 boats registered, then the expected number of manatee deaths caused by boats is negative 120. Well, first of all, how is any manatee going to be killed by, like I say, a boat propeller if there's no boats in the water? And also, how can there be a negative 120 manatee killed? See, the numbers just don't make any sense. So in that problem, you need to understand that, well, the y-intercept, doesn't have any kind of real-life application. It's important for graphing the line, which we're about to do, but not any kind of real-life application. So 0 is too far away from the real domain of 65 to 85, this data that created this regression line. Oh, by the way, if you want to see how you can take a scatter plot and from it create a least squares regression line, a linear regression model, I do that in statistics. So I'll put a link in my lesson here if you want to skip to that video and kind of see where this equation would come from given some actual real data. So, okay, so 0 is too far away from the real domain to be trustworthy. This is called extrapolation, another vocabulary that I use quite a bit in statistics. And as in algebra, as we move more and more into, let's just not do the raw math, but actually apply it to real life, becomes more important to understand that as well. All right, so let's get this graph, this linear function that's representing the relationship between the number of boats registered and the manatee deaths, just to get some practice graphing, and then just finish up our lesson with a few more definitions. Alrighty, let's get that equation graphed. We have y is equal to 2.4x minus 120. Of course, the manatee's killed again in the boat. So we have a slope of 2.4. Slope is rise over run, so we have a rise number, now we need a run number, and it's not written as a fraction, so we need to write that as 2.4 over 1. Now, I don't know about you, but I don't want to try and rise 2.4 units. I know that's somewhere between 2 and 3, but if I take this fraction and I multiply it by 10 on the numerator and denominator, I'm going to get 24 over 10, and now, after I get my initial point graphed, I can rise up 24 and run 10. My y-intercept is negative 120, and I can see that I kind of have some pretty big numbers going on here. So let's see, if I do, I don't know, how about negative 10, negative 20, negative 30, 40, 50, 60, 70, 80, 90, 100, 110, negative 120. And let's just count by tens here as well. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. And I'm going to go to that y-intercept of negative 120, and I'm going to put a dot. And then from there, I need to rise up 24 and go over 10. So I need to rise up 10, 20, that'd be 30, so somewhere in the middle, and over 10, and put a new point, and then up 24 again. Well, 24 and 24 is 48, so approximately what? Like if I think of here, another 24 would be up 24. So up 10, and another sort of 4 units gets me close to 50. 24 and 24 is 48. Let's see here. 10, 20, 30, 40, 50. Yep, I seem to be in the right spot. And then over 10 again, and looks like we're about right there, and the line looks something like this. Now, because of the scale of this problem, these values, I think it might be a little bit easier to try and graph this using x and y intercepts instead of a y-intercept and a slope, where we'd graph the y-intercept first and then we just did what the slope said. So we already know what the y-intercept is. The y-intercept you find that by letting x equal 0, and that y-intercept is equal to negative 120. And we have that point already on the y-axis. So let's find the x-intercept. The x-intercept is when y is equal to 0, and so we're going to take our equation and set it equal to, well, 0. So y is equal to 0. 2.4 x minus 120. We're going to add both sides by 120. We want to undo that subtraction of 120 to move it away from the x, and we get 120 is equal to 2.4x. And now with the x, we have a multiplication of 2.4, and we're going to undo that multiplication of 2.4 by dividing by 2.4. And that is going to give us running out of room here. X is equal to, I'm going to turn this around as well. Actually, it's not the greatest habit when you're working with inequalities. Not that this is an inequality, but 120 divided by 2.4, let me just check my notes here. That is going to come out to be 50. So our x-intercept is at 50. Now let's see here. 10, 20, 30, 40, 50 is our x-intercept. And so I was a little bit off. That is the line representing or modeling the relationship between the number of manatee killed, excuse me, got that backwards, between the number of boats registered in tens of thousands and the number of manatees killed per year. I don't really think that even that is the best sort of visualization of what's going on. It doesn't represent this information very well. We were collecting data between, I think, 91 to 2014, but that's just irrelevant because we're just looking at the relationship between the number of boats and the number of manatee. Well, the number of boats was between 65,000 and, even though I wrote this example, and 85,000. So really, the boats were between 65,000, so this is 50, 60, 70, 80, 90. It's kind of like in this really small section here. It's almost like if we had a calculator, we could zoom box and kind of see the portion of the graph that we actually need. So what I'm going to do is I'm going to step off 10, 20, 30, 40, 50, 65, 60, 70. So we need like basically a window, 65, 70, 80, 90. We need like a little window right in there. That's really the portion of this linear function that is representing the data that we used or that created this linear regression line of y is equal to 2.4x minus 120. Okay, so let's get some numbers here, and then I'm going to step off and write a new picture. We got y is equal to 2.4 times 65 minus 120, and y is equal to 2.4 times, this data was between 65,000 and 85,000 boats, so 85 for 85,000 minus 120. Let's see what those two coordinates are and redraw our picture just to focus on the part that's interesting or important to us for our word problem. So doing our little zoom box by hand, we have 65 plugged in, gave us an expected number of manatees killed per year of 36. Using that number of boats of 85 for 85,000 gives us an expected value for the manatees of 84. And we have the points of 65, 36, and 85, 84. And just zoom on this big whole, just, you know, sort of generic algebraic graph, zoom in on that portion that was relevant to our data that created that regression line. We have boats on the y-axis, manatees on the x-axis, manatees on the y-axis for that independent and dependent variable, and a graph that represents our data. And probably, you know, there was some real data that was collected that, you know, had some, well, I showed you the link in the video for the video earlier, where some kind of computer or calculator modeled a line, a least squares regression line, through that actual data, and that's what we used for our example. All right, we're going to move on to just a little bit more about increasing and decreasing. I kind of already said this a little bit, but just put it in formal language and give you a little bit more information about vertical lines, and we are going to be done with our lesson. Attributes of graphs of linear functions, well, they're either going to be increasing, decreasing, or constant. They're going to be increasing if m is positive, the slope, decreasing if the slope is negative, m, and if m is equal to 0, you're going to be looking at a constant, what's said to be constant, where x is changing and y is like saying, I don't care. And since we're talking about y equals mx plus b with all of these, for the constant equation, if you're looking at y is equal to mx plus b, and your slope is equal to 0, well then x times 0 is 0. When you add by 0, nothing really seems to happen. So when you have a constant linear function, when you have a line which is horizontal, the equation is going to just look like y is equal to b. There's no x because, again, that slope is equal to 0, and x times 0 is 0. Because linear functions forever either increase or decrease unless they're constant, linear functions do not have any kind of maximum or minimum, whether it's relative or absolute. Because our slope is constant, that's what is creating these graphs of linear functions. That's why they're straight. And except for vertical and horizontal lines, the domain and range of all are all real numbers for both. Well, I just said that, for both the domain and the range. Now, so I'm kind of hinting here a little bit that we have some special cases with lines. If you have a vertical line where only the y is changing, but the x is staying the same, that's going to be in the form of x is equal to some kind of number. And the domain for a vertical line, the domain being the x values, the input values, that's whatever that, if it's x equal to 5, then the domain is just 5, period. That's the only x that's going to be included in all the points which make up the graph. But since it goes up and down forever, the range is going to be all real numbers. If you have a horizontal line, which I just kind of hinted to why it's y equals a number, that slope is equal to 0, then, well, the equation of a horizontal line is y equals a number. It is going to be horizontal, and the domain of that is going to be all real numbers because it's going to be moving horizontally, so that line is going to contain every single possible x value that exists, but the range, what y values are going to be included in all of those individual points that make up the graph, well, that's it. Y equals a number. So I'm mentioning that horizontal and vertical lines are kind of a special case. The vertical lines are even more of a special case because the slope is undefined. And you'll notice here that I'm talking about a linear function. Every x only has one y. It's not I'm not talking about relations where a given x value can have multiple y values paired up or mapped with it. And so I mentioned that lines can be increasing, decreasing, or constant. Nor over here am I pointing out the fact that the line can be vertical. Well, a line can be vertical, but then it's not a function. It's a relation. So yes, lines can either increase, decrease, or be constant, and they can increase or decrease also in a special case so drastically that the slope is undefined. So let's get a little separate page about vertical lines, and then I'm just going to highlight a couple different forms of lines, standard form and point slope form, and we'll be done. So I'm just putting into words what I just verbally said already. Make sure you got it and it's all clear. At last, a last type of special linear graph, notice the word equations, functions gone, is in the form of x is equal to b. The line is not a function because that given value of x not only has more than one y value attached to it, which is enough to have it fail the test for being a function, but it's actually got an infinite number of y values paired up with that x value of 3 in this particular example. Slope is rise over run, and to get from one point to another, there is no run, and you can't divide by 0, so thus that slope is going to be undefined. You can, I just said that. You cannot divide by 0, so the slope is undefined. In the example of graphing x is equal to 3, notice there's no y in this equation because we don't care what y is. Not for the line x is equal to 3, or x is equal to 0, or x is equal to negative 10. The only requirement for that line to represent that equation is that every point on that line has the same x-coordinate, and that x-coordinate is 3. Y can be anything. That's why it goes up and down forever. The other forms of linear equations, we have the standard form. Don't honestly use this particular form very much, but it's ax plus by is equal to c, and a, b, and c, by definition, all have to be integers. So if one of those were a decimal or a fraction, you'd have to multiply or manipulate that equation somehow, probably through multiplication, to make those fractions or decimals, sorry for the static, disappear. And then we have point slope form. Y minus y sub 1 is equal to m times x minus x sub 1. If you look at my other lessons about coming up with or writing the equation of a line that's parallel or perpendicular to another line, or if given 2 points with the equation of a line, I like this form a lot. This is my favorite to work with for, it shows you that the minimum that you need is a point and a slope. If you have a point, x and y, and a slope, then you can write or come up with the equation of that line. So I'm Mr. True. Bam! Go do your homework.